Hey everyone, this is Muhammad Nadeem and welcome to my YouTube channel. Today in this video we will discuss in more detail about thermistor. I hope you may see such shape-like devices in circuit. So if it is present in the circuit, so it must have some functionality inside that circuit. So this type of device you see in the circuit is called thermistor, and as the word of this thermistor indicate us that therm mean temperature and mistor is come from the resistor. So this the relation of the resistor and the temperature, relation of temperature and resistance. This relation between the temperature and resistance is different for different nature of material. So let's say we select the conductor and then we go to see this relationship for the insulators, and then we will see this for the semiconductor. So first we will see the relationship between the temperature and resistance, and such type of relation we discussed in the previous videos. So here is the direct relation between the resistance and temperature. So R is directly proportional to temperature. Let's say we have this rod, and this rod is actually a conductor, and this will made up of large number of let's say this rod is copper rod. So this rod will made up of large number of copper atoms, and there will be large number of free electrons. And during the if we increase the temperature of this rod by providing the external energy, then the collision, then the oscillation of the atoms, of the copper atoms, will be more due to their vibration, due to increasing the kinetic energy of the the copper atoms. Their vibration is more, and due to the more vibration, the probability of the collision of the free electrons with the atoms or other free electrons will be more. Therefore during collision heat is produced, and that heat is called resistance. So by increasing the temperature, the resistance of the conductor is increased. So in this case so this is this case for the conductor. Now for the insulator, this resistance is not directly proportional to temperature, but this is inversely proportional to temperature. Here I mean that if we increase the temperature of insulator, then their resistance is decreased. Inside the insulator, the atoms are the electrons in the atoms are arranged in such a way that electrons are tightly bound towards this nucleus. So if this electron present here in the insulator, these electrons will be tightly bound to this positive charge, this nucleus. Therefore the electrostatic force of attraction on this electron will be more, and this electron will not free from the atoms. So if there is no free electrons, then the current passed through this material will be low, or there will be no current. So therefore we call such material is called insulator. If we explain this by band gaps, so this insulator have the band gap. So it will have some valence band, and this is the conduction band. So the gap, the band gap, so this is the actually the conduction band. So there must be gap between the valence band and the conduction band. So in case of insulator, that band gap is very high. The electrons are mostly present in this valence band. It do not jumps to the conduction band. So mean the resistance in the in such material will be high. And the same explanation is for the semiconductor. So the band gap of, so from here we conclude that the band gap of conductor is less than the band gap of the insulator. Band gap of insulator, and which is less than the band gap of semiconductor. So if the electrons are present in the valence band and it is not in the conduction band, therefore their resistance is very high. In this case, if we provide the temperature, so here if we provide the external temperature, these electrons will get energy and it will jump to the conduction band. Now the resistance of this atom of this material will be less, and there will be some electrons present in the conduction band. So that electrons come due to temperature. Therefore we say that if we increase the temperature, the resistance will increase. So here as we discuss that in the insulator the electrons are tightly bound to the nucleus, and if we provide the external energy to it, then that electron give extra energy from this external energy, and due to which it free from the atom. So now that electron which is free from the atoms is a free electron, and which will take part in the conduction. So this is the free electrons, and that will take part in the conduction. This same explanation is hold for semiconductor, because semiconductor is present, the band gap of the semiconductor is present between the conductor and insulator. So in this case the electrons are still bound toward the nucleus, and they are not free, but not so tightly bound as compared to the insulator, and not so free as compared to the conductor. So this is present in between insulator and conductor. So this was explanation about the relationship of the resistance and temperature in different nature of material. So positive temperature coefficient. We also call this as P positive, T temperature, and C coefficient. So now we will discuss that what is PTC, positive temperature coefficient. Positive temperature coefficient mean that just like in the conductor, R is directly proportional to T. So in positive temperature coefficient are the material in which the resistance of the material increase with increase in temperature. So the positive temperature coefficient will be present in the conductor. Negative temperature coefficient. We call this N for negative, T for temperature, and C for coefficient. So in the negative temperature coefficient are the case of the insulator and semiconductor, in which the resistance is inversely proportional to T. By increasing the temperature, their resistance will be decreased. So here in this case the R is inversely proportional to T. i.e. in conductor or insulator. NTC is occur, and this is for the conductor. This is for the conductor. Now we are in position that we can distinguish between the materials such as conductor, insulator and resistance with regards of the relationship between the temperature and resistance. Now we will discuss the construction of this material. So here we have this material, and I am going to give the topic here, the construction. This material is look like here will consist of the metal oxides such as copper oxide, nickel oxide, zinc oxide. That oxide will be present in the form of powder, will be present inside this material. So here this gray like shape is actually that the metal oxides, and that metal oxide may be copper oxide, nickel oxide, zinc oxide and so on. Different oxides based on their preparation process, these oxides are mostly nanomaterials. They are mostly nanomaterials, and we know that the nanomaterials have the range. Nanomaterials have range from 1 nanometer to 100 nanometer. So these are nanomaterials. So if the material comes in the nanoscales, then their band gap will increase. So in this case they have different band gap, and that band gap depends upon the different process in which this material by the process on which that material is made up of. Also depend upon the precursor and many more things. So here what I am going to say is that this thermistor is made up of that metal oxides, and that metal oxides are connected through this conductor to the outside. So if we increase the temperature here, if we have two type of this material. One is the PTC, positive temperature coefficient. So PTC, positive temperature coefficient thermistor. Those metal oxides will be present whose band gap is very less. So if such metal oxides whose band gap is very less is present inside this thermistor, then this thermistor will behave as PTC, positive temperature coefficient. Mean that if this will use as a sensor device. And similarly, the second type of the thermistor is NTC thermistor. This is the type of thermistor which is made up of the material here, in this case let's say the metal oxides, but in this case in this thermistor the band gap of that material will be greater. So in this case if we increase the temperature, the electrons will jump from the valence band to conduction band, and due to which the current will flow.